All right, so just kind of want to, this week we're talking about, it's an introduction to the course, but we're really talking about analog and digital, the terms analog and digital and how it applies to logic. And I'm going to share with you now the list of objectives for week one. So we kind of see what we want to know by the end of this week by Friday. So take a look at the document I'm sharing with you, and then we either will have or we will talk about these points. But by the end of Friday, by the end of the day Friday, you should understand the difference between a PC and a PLC. We haven't really talked a lot about the PLC, but we'll get into that. We want to talk about and understand what we mean when we use the term analog and when we use the term digital. What do we mean by analog and what do we mean by digital? We'll look at analog and digital quantities and we will compare them, and we'll talk about some examples or advantages that digital has over analog. Once we define what we mean by analog and digital, we'll talk about something called the digital advantage. We'll show some examples, and then I've used this term in the last class when we were talking about truth tables. I mentioned the fact that when switches are open or closed, we can talk about the state of a switch being open, call that false. The state of it being closed, we call that true. But in reality, what we use when we represent a switch open or being open or closed, we use what we call a binary number, 0 or 1. So we'll talk about what we mean by binary. We'll define what a binary number is. We call a binary number a bit. We'll talk about the type of binary numbers. We'll name the bits. So we'll go through each of these points, point by point, and then there's some terms down here that you want to make sure that by the end of the day on Friday, that you are familiar with those terms. So I'm going to move over to the topic sheet. So pretty much every class you'll have, if I don't have a PowerPoint that I'm talking about, you'll have this sheet, which is kind of an outline of the points we're going to talk about. So today's topic, we want to understand this idea of or concept or definition of what we mean by analog and what we mean by digital. But before we do that, let's review some really basic stuff that we talked about in the last class. And so we started the last class, I asked the question is, what's the difference between a switch and a button? And then we looked at several kinds of switches. We were able to name a switch depending on, you name a switch by the number of what we call the pole. The pole is a part of the switch that makes a connection with the contact. And you can name a switch by the number of poles it has and the number of ways you can move the pole to touch a contact. And so we did some examples of that. By the way, if you guys miss any lecture, usually at the end of the week, hopefully by Sunday, I will post the link to the record. I do record all these lectures, and I put it up on YouTube. So I'll post the link to those recordings. I try to get it by Sunday night for the whole week. If for some reason you need it faster than what I'm providing it to you for or at, then just ask me, send me a text, and I'll try to get it up if you got to get it right away. But just want you to be aware, there's a link at the bottom of your homepage that says past lectures. If you click on that, you'll see links to all the previous lectures, and we don't have any yet, but by Sunday I'll put those links up there. So in the last class, we talked about types of switches, we talked about buttons, and we talked about this idea of a button being normally open and normally closed. So I just want to review that real quick. We have this switch. This is the simplest switch that we have, and this switch is going to represent for us what we call an input. And that switch can be open or closed. We say it's true or false. If the switch is open, we can say it's false. If it's closed, we can say it's true. We talk about the input. Now, it can get a little bit confusing because the term input you can use in reference to a switch, or you can use in reference to a signal. You can think of it either way. And usually it'll be clear from the context of the situation. You can't see anything. You guys can't see me?
No, no.
I can see you. I just had to click
I can
on,
see you.
like, your little profile thing.
Oh, okay. Okay, so when the document is up, guys, when the document is up, I can do this and I can remove it, but you can do the same thing. You should be able to click off the document. As long as I'm sharing my camera, you should be able to click close that document on your screen and it'll bring the camera up. Now, if I lock the camera out, you can't do that. So I just forgot to move it over. So I'm showing you, this is a single pole, single throw switch. We call that an input. And when I use the term input, I can use it to reference a switch, or I can use it to reference a signal. And it'll be clear from the context of whatever problem we're talking about, which I'm referring to. So we got a switch, and then we got a button. But I showed you the button two different ways. I can have a button like this, or I can have a button like this. And remember, the way the button functions is there's a little spring here pushing up on that pole, and there's a spring here pushing up on that pole. And here, if that spring is pushing up on it, it's actually keeping the pole separated from the contact. So if you took that switch and laid it on the table, the spring will keep the pole and the contact separated. That's called the normal state. Normal state means no human interaction. So in this normal state, this button is open, and so we call that a normally open. It's a push button. And this works the opposite way. This time the spring is keeping the contact and the poles together. And so if I lay this on the table, no human interaction, this switch, we call that a normally closed push button. So the state of either a button or a switch being normally open or normally closed is important to know that. So that's one thing we talked about that's important in the last class. The most important thing, though, we talked about is the ability of taking just a basic circuit and having it make decisions for us. And there's, well, a better word would be logic. There's logic we can use. We can build logic circuits, basic logic circuit with switches and buttons. And so we talked about the three basic ones. And the three basic types of logic would be AND logic, OR logic, and NOT logic. So I showed you in the last class some simple circuits you can put together to demonstrate how AND logic functions, OR and NOT. And just briefly, just real quick, if I have switches and they're connected in series, and you know from your circuits class, that means they're connected end to end. Now, if I have AND logic or OR logic, I got to have at least two inputs, two switches or two signals. This is the only one where it works on one input. So for AND logic, what we did, we took two switches, we hooked them up like this. This is what I mean by series. And if I have something over here I want to control, like a motor or a light bulb or whatever, and I have some kind of power source for that motor, and this is input A, this is input B, the only way for me to turn that thing on over here, the motor, is both switches have to be closed. So I got to close switch A and switch B. If A is true or closed, if B is true or closed, then the output over here, the motor turns on, we say it's true. So if I showed the state of this in the table called the truth table, you can look at the last video to see what that looks like. But for this particular logical function, the AND logic, in order for AND logic to be true, both inputs have to be true. And I get an output. So we talked about that. And then we said, all right, what's the difference between AND and OR? Well, OR works a different way. OR, I have to rewire this for OR. And we wire it like this. So if you remember from your circuits course, I have them in series to demonstrate AND logic. Well, now switch A and B are in parallel. So think about current flowing in the circuit. Current flows from the voltage source. If I close either switch or both switches, this motor is going to turn on. So the way, if you think about the truth table, what that would look like, for OR logic, if either input A or B is true, or if they're both true, then I get an output. The only way for this not to come on is for both inputs to be off. We looked at the truth table and compared them, and you saw that both of these were kind of exact opposites of each other. So the and or logic. And then we had not logic, which was kind of weird, but we had to use a normally closed push button. We had this. So that's a normally closed push button. And then we think about not logic like this. We say if the button is not pressed, then I get an output over here. If I press that button and the contacts and the poles are separated because you're pressing the button, then this thing won't work. Now, that's a little hard to understand. It becomes a little easier when we actually talk about binary, because what this is going to end up doing is reversing the truth or falsity of something, or reversing bits, and we'll get to that later on. So that's kind of a brief review. But what is it that we're sensing? What is it that when I talk about an input, what is it that we're controlling? Well, let me back up a little bit, and I want you to think about something. What we're trying to do is make electrical circuits make decisions for us. And I can take these basic, just like in chemistry, you can take basic elements and make a chemical and compounds and get more complex from that. Logic works exactly the same way. These are like our basic elements, and or not. From these, I can build more complex logical circuits, and in theory, I can have enough of these hooked up together to control almost any kind of complex operation. Now remember, when I went from the AND logic to the OR logic, what I had to do, I had to go in and rewire those switches. I had to go from series to parallel. Well, the other thing we talked about in the last class was a relay. I went through and I showed you kind of a picture of a relay, and we talked about how relays work. You'll do your first quiz assignment. It's going to deal with relays. You're going to watch a video, and then you'll talk about what you learned about in the video as to do with relays. So really, even though I'm showing switches in series and buttons, really we're doing the same thing with relay contacts, but it's easier to think of them in terms of switches. So in the old days, they would hook up relay contacts in parallel, relay contacts in series. They had ways they could invert or not the inputs to build these really complex circuits to control like an automobile factory. That's not the way we do it today. I had to go in and physically rewire the circuit, and this was a simple circuit, just a 2-input AND. Imagine your General Motors, and you have some kind of process where you may have 1,000 relay contacts hooked in the combination of series and parallel. It used to be a nightmare, and in your first homework, you go back and you'll study how things were before PLCs, and you'll look at the first PLC and when that was introduced. But back in the day, it was all done with hardware, all done with relay contacts. If you were General Motors, now they don't do it so much anymore, but back in the old days, I'm talking even when I was a kid, I can remember the automobile body would change about every other year. I think now body stays the same for quite a while. But back in, let's say, I don't know, maybe the 70s, maybe you might have a car model from 70 to 72, and then after 72, the body style would change. Well, from an engineering point of view, you had to go in and maybe on the bumper on the old model, it took 4 screws. Maybe the new one might take 3 or 6. I don't know. There's some kind of difference. What you'd have to do is you have to go in and have an electrician go in and manually rewire the logic circuits. That took a lot of time, and you can imagine if you have a whole lot of relay contacts all hooked up in series and parallel in different configurations, the possibility of making a mistake was often they made mistakes. So then this idea of removing the logic part of a control system, and instead of having actual hardwired switches or relays control processes or devices, we can do the same thing in software. And that's where the PLC comes in. And so we'll talk about the PLC. So we'll come back to the PLC, because what we want to understand is the difference between a PLC and a computer. For now, think of a PLC as just a heavy-duty computer. And by heavy-duty, what I mean is this. It's a computer designed for use in the industrial environment. And we'll get into some more details of that. Before we get into that, though, I want to talk about something that's really important to understanding PLCs and how to use them. There's 2 terms. One is analog, and the other is digital. So I want to talk about what we mean by analog and digital, and I want to tell you why it's important to understand what these terms mean and what we do with them. So what I'm leaving off is the term signal. So if you're writing, if you're taking notes, when we say analog and digital, you hear these words used all the time. You hear them used all the time, but what we really mean is analog signal and digital signal. Now, what do we mean by signal? What's the signal? Well, electrical devices can only understand two things. Electrical devices can only understand or see voltage or current. Voltage or current. Just to keep things simple, think of voltage as electrical force and think of current as the flow of electricity or the flow of electrons. And there's a cause and effect relationship between voltage and current. Now, I don't mean to go back to your circuits course that you've hopefully already had, but just suffice it to say that if I have anything electrical, any kind of input, and I want to get some information into that device, I either have to do it with the voltage or I got to do it with a current. That's the only thing that we can see. It can see. So when we talk about a signal, we mean a voltage signal or a current signal. Either one, the way you think about it right now, isn't important. What is important is the type of signal we have. We can have an analog signal or we can have a digital signal. So here's the definition of both. Or here's how you can distinguish one from the other. Analog means continuous. Analog means continuous. So if I have a continuous current or a continuous voltage signal, then that would be an analog signal. Analog means continuous. Digital means discrete. Discrete. And the best way to really understand that is to kind of just think about an example. Now, before I talk about the example, I want you to think about physical quantities. Physical quantities. And it turns out that most physical quantities in nature are analog. They're continual, at least the ones that we'll measure in this class. So what do you think the most measured physical quantity is on the planet Earth? What's the number one most measured physical quantity on the planet? What physical quantity do we measure most? Anybody?
Money.
You would think so. Probably money might be the second. I don't know, but you think it. But not everybody values money. There's civilizations that. So what's
weight
the
or something?
weight, mass? About this. Time. Time is the most measured quantity on the planet. And time is, as you know, time doesn't jump from it's not finite. It doesn't jump from one time to another. It's smooth. Another quantity we might measure is temperature. Say you're going to measure the temperature, and you get up in the morning. You're not using your cell phone to do this. You actually have a thermometer. You look at the thermometer, and you see you get up in the morning. It's 42 degrees outside. If you watch that thermometer, if you made a graph of the temperature, let's do that. Let's make a graph of the temperature. If you make a graph of the temperature versus time for maybe like a day. So I got, on this axis, I got time in hours. And on this axis, I got the temp. We'll say degrees Fahrenheit. It doesn't really matter. So, and maybe right here, maybe you get up. Uh-oh. Hold on, guys. I'm in a room with a motion detector in it, and I guess it can't pick me up because I'm over on the corner. And so it just turned the lights out on me. If you saw it go dark, that's what happened. So let's say that you get up, I don't know what time you get up. Let's just say you get up at 8 a.m. So right here, we'll start that at 8 a.m. And you're going to measure it over here till, I don't know, let's say 12 a.m. And at 8 a.m., you look at the thermometer, and it's like at 42 degrees. Now, you know that the temperature increases, and it doesn't go from 1 degree point to the other. It kind of smoothly, there's a gradient, there's a transition. So it might warm up as you get towards noon. It might stay at a certain level for a while, and then it might cool off during the evening. So notice I'm not lifting my marker from the board. What we like to do is, if I want to record this electronically, I can represent this temperature. I can only do it two ways. I can either use a current to represent it or a voltage to represent it. No matter which of the two I use to represent it, that voltage or current is going to be continuous when I represent this, when I take a copy of it. And so this would be what I call an analog signal. Whatever I use to turn that temperature into a voltage or to turn that temperature into a current, that current or that voltage is going to be continuous. It's going to follow the continuous flow of this. And this is what I mean by analog. So most devices will measure, not devices, but most quantities we measure in nature are analog. So if you think of sound, that's analog. If you think of pressure, typically it's analog. Definitely time and temperature, these are analog quantities. And it's safe to say that most quantities we will measure or we will use as an input for PLC, they're going to be analog in nature. Not all, because maybe we want to know if something's there or not there. In that case, it's not analog. But most of the physical quantities we measure in nature are themselves analog. So this will be an example of an analog signal or analog situation. Well, if this is analog, how does this compare to digital? What do we mean by digital? So digital is a type of electronics. There's two sides to the electrical house. There's the analog side where we deal with continuous signals, and then there's the digital side where we break things up and we give values we give points certain values. So let me get into what I'm saying here. So I want you to imagine that instead of having this continuous graph, which you couldn't record this graph anyway, because you have to stand there and look at the thermometer from 8 a.m. all the way till 12 a.m., which that's not possible. But what you could do is you could say, well, I think I'm gonna look at it every hour. So you go in and you look at it at this time and at this time and at this time and at this time. Every hour or maybe every half hour, you go in and you look and you take a temperature. So maybe at this time, you'd have that point right there. At this time, you'd have that point right there. At this time, you'd have that point right there. You do that. You take these samples of this signal over these regular time intervals. And what you would end up with is kind of like one of those graphs where you connect the dots. What you would end up with, instead of a nice continuous graph like that, what you would end up with is this. You'll end up with a data point here, 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 and a data point here. So this right here represents this is an analog representation of temperature. But down here, I've done something different. I've actually went in here and I've took these points right here. I've took samples of certain points at regular times, and I got these samples down here, and this recording those as data points. Now let me go to another graph that I want to share with you on screen, because I think it works a little bit better. So what I'm trying to do now is, I think it's pretty easy, pretty clear to understand what analog is, but understanding digital is kind of a process. It might not be what you think. So let me show you this other graph. Take a look at this. All right, so at the very top graph, you have pretty much what I was describing. This could be a voltage or current over time. And whatever it is, you can see it's increasing and decreasing. It's continuous in nature. So maybe this is a sound wave of a particular frequency. Doesn't really matter what it is. The point is that whatever this voltage signal or current signal is representing, notice that it's continuous over the whole time. If I want to digitize this signal, then I got to do what I showed you on the board. What I showed you on the board, let me switch away from this. What I showed you on the board is, if I want to take this analog signal and turn it into a digital signal, the first thing I got to do is I got to take samples of the analog signal. So I'm going to sample the signal. I'm going to sample it here. When you sample an analog signal, you do it over regular intervals. Now we're doing it over hours, but in reality it's done in microseconds or milliseconds, or it's done really, really fast. The point is, we start with an analog signal. We take readings, or we take samples at regular intervals, and then what I'm going to do is just grab those samples that I made. So if I go back to the diagram that I was showing you before, notice that I have an analog signal at the top, but what are we doing at the bottom down here? What we've done is we've sampled different points. Maybe we sample a point right here. We sample points throughout. At the very bottom, they're showing you that we got a sample here, we got a sample here, we got a sample there. We sample that analog signal all the way out through that time as indicated in the graph. The graph at the bottom does not represent the digital quantity though. There's another step you have to do. And the other step is this. Notice over here on the left, you have these zeros and ones. Zeros and ones. So the 0 and the 1 represent something we call binary. Binary. So let me switch off the camera and let me talk about that. So here's how it works. And all digital devices work this way. It doesn't matter if it's a computer, a cell phone, doesn't matter what it is, it works the way I'm about to explain. If you think about that, a device, I'll call it a digital device for now, but I'm really talking about computers. But my definition of a computer might not be what you think. The only thing a digital device can understand is the presence or absence of a voltage or current. So we just focus on voltage for a minute. I can have a voltage or I cannot have a voltage. And typically, just to talk about a value, I'm going to use 0 volts and 5 volts. So typically, we use 0 volts and 5 volts. So I can have a voltage of 5 volts, or I can have a voltage of 0 volts. What digital electronics is called is two-state electronics. Instead of having a whole value that voltage or current, a whole range of values that voltage or current can take, you can only have 2 values. If we're talking voltage, 2 values of voltage or 2 values of current. So we're going to use 5 volts and 0 volts. And instead of dealing with voltage, just to kind of abstract from that, what we're going to say is if I have 5 volts in this system I'm talking about, we're going to call that a 1. We're going to give it a value of 1. And if I have 0 volts here, we're going to give it a value of 0. Now, let me talk about what I mean. What is the 1 and the 0? So this is what we call binary. I'm running out of room here, but I'll squeeze it in here. This is called binary. And we're going to study, I think next week or in a couple of weeks, we'll study binary. We'll study binary numbers in much detail. But all this is a kind of a numbering system that computers use. Anything, and when I say computers, I mean any digital device like your cell phone, anything that you can process information is doing it with binary. And so binary is just two-state electronics that uses one voltage or another instead of a whole range of voltage. And you probably already heard about the zeros and 1 thing. You might not have ever known what it meant. But 1 is the presence of some value of voltage, and 0 is the absence of some value of voltage. It doesn't really have to be 0. It's just got to be different than this one. I could use 5 volts and 4 volts if I want to. It's just got to be different. But typically, we use 5 volts to represent a 1, 0 volts to represent a 0, a binary 0. So binary is just kind of a number system that deals with 2s, just 2 things. You might say, well, why use that? Well, we use, when we think about the number system that we use as humans, we use a base 10 number system. We use a decimal, deci means 10. And the reason we do that is when we count, we have 10 digits. We got 10 fingers, 10 toes. Well, computers, digital devices, they don't have 10 fingers. They have 2. And what do you mean by that? What I mean is they're built with switches, those and or circuits we talked about. And the switch can either be open or closed, one state or another. So this two-state electronics that we're talking about really fits perfectly for digital devices. For those kind of devices, they're two-state devices. And so I can have a switch that's either open or closed, so I can represent the state of that switch as a 1 or a 0. Or the state of any binary system is going to be in one state or another. I can represent those states as a 1 or a 0. And so if I take a 1 or a 0, what they did is they took the term binary. A 1 is a binary digit. So the 1 is a binary digit. The 0 is a binary digit. And then what they did is some smart person, they took the BI from right here, the BI, and they took the T from here, the T, they came up with this name bit. So a bit is just short for binary digit. And so that 1, it's not 1 volt, it's a binary number 1. And that 0 was not 0 volt, it's a binary number 0. And you're going to see we can actually do a lot of stuff with this binary. We can do math, we can do pretty much anything you can do with regular numbers, we can do with these. But right now what we're trying to do with these is go from a analog signal to a binary or digital signal. And so I was showing you that on the screen. So let me go back to that diagram, and this will make a little bit more sense now. So in this diagram, if you go to that first graph at the top, I don't know, this could be sound, whatever you want this to be. We got some kind of analog signal at the top. And what I want to do is change that analog signal to a digital signal. I want to digitize the signal. I want to digitize it. I want to talk about why we want to do this in a second, but I'm going to show you how we do it right now. So what I have to do is I have to take samples. And so you have some kind of circuit that maybe takes a sample here, takes a sample here. They're showing you in the bottom graph here all these samples. Here's a sample point right here. And here's a sample point right here. And you'll see that these time intervals at the bottom, they sample at regular intervals. And what they end up with is a bunch of dots. But notice these numbers over to the left. When you digitize a signal, what you mean by digital is you actually take one of these points, like this one right here, or let's do one that actually has. So this one right here corresponds to this set of ones right there. It's a 1, 1, 1, 1. It's a whole series of ones, whereas this one maybe right here corresponds to all these ones with a 0 at the end. The point that this picture is trying to make is each one of these points on this graph is given a code, not just any code, but a code consisting of 0s or 1s. It's given a binary code. And when you store any kind of information in binary, you're not storing the information itself. What you're storing is a group of 0s or 1s that represent each piece of this analog signal, this analog current or voltage. So let me switch away back to the camera because I want to make sure you understand this. So in order to digitize, say this is the temperature or sound, whatever it is, it doesn't matter. If I want to store that point right there, well, I sample the point. Here's a sample of it. But then what I got to do is I got to give this a value, and that value is going to be a binary. So maybe that point has a binary representation like this. And then this point has another binary representation maybe like that. It'll be the equal number of bits, but each individual point has its own code, and that code is unique to that point. And if you were going to store this information, if you're going to store this, you got to store the actual voltage or the actual, some kind of way you got to store it magnetically, or you got to store the actual infinite value of points. Here, you're just storing the code right here. You're just storing the 0s and 1s. So I said in the beginning of this discussion that analog means continuous. That's kind of easy to see. I can draw a sound wave. This example was with temperature. You pretty much understand that we have continuous values that go from one to the other. But if I want to take that signal and I want to digitize it, I got to do a whole lot of work to go from an analog system to a digital system. Well, okay, well, why would we want to do that? I mean, why go through all this? It seems like a lot to sample these points and then to take each point, assign a value to it. Now I got to store these values. And why would I want to do that? Well, let me give you a couple other examples and then I'll tell you why. Now, I don't know what kind of music you guys listen to. I like all kind of music, but I guess you know the artist Lil Wayne. So if you know Lil Wayne, I don't know if you guys know what a cassette tape. Who's that? That's only one person has their picture up. Brian, you know what a cassette tape is? Anybody know what a cassette tape is?
Yeah.
Yeah.
I know what a cassette tape is. But we're
Right.
old enough to know.
Yeah, so back in the day, like when I was probably a little younger than you, if we wanted to record music, you'd have a cassette tape is like, basically it has a wheel in it and there's plastic with the chemical compound for rust, basically rust. And they coat this plastic with this rust compound and then they're able to record music on it magnetically. It's analog, it's recorded magnetically. But here's the problem with it. Let's say that I have this tape, Lil Wayne tape. I got it from the store, and when we made copies back in the day, I don't know what term you guys use now. We said we're gonna dub it. That means, hey man, I want a copy of your tape. So my buddy might say, I want to make a copy of that. Let me dub that tape, Ron. Say, all right, man, I'll give you this tape. You better give me my tape back. I want it back in one day. So he would take it, put it in his machine, and he would make a copy of it, give me the original back. And maybe he has a friend he's listening to Lil Wayne and saying, you know what, I think I want a copy of that. He gives it to his friend. And it keeps on going down the line. You make a copy of a copy of a copy of a copy. If you make a copy of a copy of a copy of a copy of anything analog, every time you make a copy, that next copy, we say that's one generation away. For every generation you get away from the original, you lose quality. If you made 1,000 copies of that Lil Wayne tape, by the time you got to the 1,000th person, if you put the original, we'll call the original the master. If you put the master in the machine and listen to it, and you take the one that's 1,000 generations away and you put it in there, they're not going to sound the same. Matter of fact, the one that's been copied 1,000 times, it's going to sound like, well, I'm not going to say it, but it begins with the S, ends with the T, and it has a H and an I in it. It's going to sound really bad. So the big problem with analog signals is that if you make a copy of a copy of a copy, the signal quality degrades. It degrades. That does not happen with digital, because with digital, you're not storing the actual signal, you're storing a code. You're storing a group of zeros and ones that represents a certain value. So if you were to play this back, you would actually, these zeros and ones determine what data point you're getting back, and this 11000 is the same no matter how many times you repeat it. So one reason we like to digitize information, not the only reason, is that digital doesn't degrade. Analog degrades over time, or if you make a copy of a copy of a copy, digital does not degrade. That's part of what we call the digital advantage. There's another reason I want to talk about. The other reason is, now those cassette tapes that I was talking about, I don't know, maybe we had them back in the 80s. I was probably, I don't know, I got out of high school in the 80s, graduated from college in the 90s. So we would have these tapes, but when you recorded music on the tape, you can get a 30-minute tape, you can get a 60-minute tape, and you can get a 90-minute tape. You couldn't go much above a 90-minute tape because tapes they had a fixed dimensions, and as the wheels got more and more tape on them, there was a limit to how much tape you can have inside that little case. And so ultimately, you were limited to the number of songs you could put on a cassette tape. Well, you guys nowadays, you can have, think about a thumb drive, a flash drive. So if you look at right now, do I have my flash drive? Let me draw a flash drive on the board. So let's say this is your flash drive. And this part right here is the part you plug into the computer. Has anybody ever opened one of these up to see what was inside of it? Anybody ever done that? If you have an old flash drive one day, just take it apart and look at the inside of it. Here's what you'll find. If you open this up, you'll find some connecting wires going in here, but you'll find a little bitty, they call it a PCB. That stands for printed circuit board. There's a little bitty printed circuit board in there, and on that little bitty printed circuit board, you will find a little square flat thing. I don't know, it's tiny. And there's some other electronics in there, but the main thing in there, so it's usually black or gray in color, it's called an IC. That stands for integrated circuit. Now, think about, I don't know what they're up to now, but I got my first computer, it was a Windows 98 machine. So I graduated from college in 96, I'm old. And I got my first computer in 98. I was using Windows 98. And when I got that first computer, the hard drive in the computer was 500 megabytes. Now, you couldn't tell me nothing. That was the Cadillac of computers back in the day. I had a 500 megabyte hard drive. And the hard drive was probably about yay big, right? The hard drive, 500 megabytes. Well, when you use your flash drive, and I know these flash drives are gigabytes, and I don't know if they're up to terabytes yet, but the actual thing that you're putting those zeros and ones in is not this big. It's like that. It's probably 100 times smaller than the thing that you're holding. And the only reason you can do that is because, number one, if it was an analog system, it would never, ever be that small. But number one, we're using these zeros and ones that I'm trying to tell you about. But number two, more importantly, we can take information with digital and we can make it smaller. We call that compressing it. You can compress digital. You can compress analog a little bit, but for all practical purposes, you cannot compress analog. So whereas on that cassette tape I was talking about, you might 90 minutes of music back in the late 80s or early 90s, I don't know, that might be, a song was longer than they are now. You know, it might be 8 or 9 minutes for a song. At max, you might be able to get 10 songs on a cassette. Now, songs are a lot shorter now, but you know, you can put thousands and thousands and thousands of the same songs in this little thing right here. So comparing analog to digital, the digital advantage, number one, I can make as many copies as I want. The original copy and the nth generation will be almost exactly alike. Digital does not degrade. And number two, I can compress digital information. I can put a lot of digital information in a really, really small place. You can take that hard drive from my Windows 98 machine and take your thumb drive and take it apart and look at that little tiny IC chip. You can put my whole hard drive on there many, many, many times over and over and over again. So it's pretty amazing. So the digital advantage, I'll ask about that. What is the digital advantage? What advantage does digital have over analog? Number one, we can make as many digital copies as we want. Digital copies do not degrade. Number two, we can compress digital, so I get a lot of information in a small space. Well, it not only works, it works with anything. So I want you to think now, your cell phone. Let's go with that for a second. Your cell phone. Let's think about your cell phone. What is a computer? I mean, that's kind of a hard thing to talk about, but when you think of a computer, what is it? What is a computer?
Is it something that does like basic mathematical functions?
Okay. Definitely that's one aspect of a computer. It's got to be able to take data and do mathematical operations with it. What else?
It can take inputs and then like process them and then turn them into outputs.
Ooh, I like that. It can take inputs, it processes the inputs, and puts out some kind of output. So the thing coming into the thing that we're calling a computer The thing coming into it, well, that's we call that data. And the thing coming out of it after it's processed, we call that information. So a computer takes data and turns it into information. Well, really anything, when I think of a computer, I got, well, right here, you can't see it, but I got a PC right here. And in my office, I have a laptop. And the one thing that laptop and that PC right here, and even your cell phone that you have in your pocket or in your table, the one thing they have in common is all those devices have what's called a microprocessor in it. The microprocessor is a computer. The microprocessor is a computer. So it's safe to say then, anything that contains a microprocessor is a computer. But guess what? Not only does my laptop and that PC right there and your cell phone have a microprocessor in it, your refrigerator has a microprocessor in it. If you have a late model car, your car probably has several microprocessors in it. If you have a microwave that you can program, it has a microprocessor in it. So while average people, or I should say lay people, think of computers as their laptop, your cell phone is not a phone. Your cell phone is a computer. And all computers, anything that contains a microprocessor can only understand one thing. They can only understand digital. So anything I wanted to go inside of a microprocessor has to be digitized. That's the example I just went through. It has to go through that process of going from analog to digital. Now think about what I'm saying. Right now you're looking at me, and I'm using this camera as a Microsoft, some kind of Microsoft camera with a microphone built in the top of it. You're looking at me. Well, light's hitting me and going into the lens of the camera. Sound is coming into the microphone. The light hitting me and the sound going into the microphone, those are all analog. The camera takes in analog and sends it into the computer, and that computer has to, before it can do anything with that data, it has to change the analog into digital. It has to change it to zeros and ones. That's all it can understand. Think about if you have either a flat panel TV. So let's go with that for a second. So on the TV, they want to build a picture. This isn't working. They want to build a picture. So they actually have little tiny cells here to make the picture. If you were to look really close at the screen, you see little tiny cells there. And those cells are called pixels. And each pixel is almost like a microscopic part of a picture. But each one of those pixels gives light information, and each pixel is represented by a group of zeros and ones, just like in the previous example I talked about. So anything that's analog that's going into a machine that has a microprocessor in it, that has to be changed from a continuous signal to a signal that's discrete, and that discrete signal is going to be represented as zeros and ones. So let me go back to this other. I'm getting off topic here, but this is kind of interesting. I want you to think about this. So remember my original diagram when I had something like this, right? Oh, there's my lights again. This is not going to work out for me. I'm running out of time, but let me just, one more concept I want to mention that's important for digital circuits, or digital, to understand digital. Remember, this analog signal contains information. Music, temperature, whatever it is, it doesn't matter. It contains information. But when you digitize it, what you do is you say, all right, I'm going to sample the point right here. I'm going to sample the point right here. I'm going to sample this at regular intervals. And then when I rebuild this down here, what I end up with is a graph like this. I've got this data point right here, and then here, and I got something like this, where if you connected the dots, you get this thing back. Now, what I want you to do for a second is just focus on that part right there. What you have is, you got that data point, you got this data point, and this line in between this data point and that one represents all that analog information. this line right here. But notice when you go from this picture to this one, you throw all that information away. All of this information in here is thrown away. Is that good or bad? Is it good or bad?
It's like good because you don't want to keep all that information, but it's also bad because sometimes you might need it.
Okay. So let's say that's a good. I like the way he said that. He said it's good because you can kind of we wouldn't be talking about if it wasn't good. But it seems like we're throwing something away that we might need. How would I get a better? What if I don't want to throw away as much information? What if I want to save a little bit more information? Not everything, but what can I do to this graph to where I can save a little bit more information than what I have here?
Increase the sampling time.
Yeah, exactly. I would sample it at a higher rate. Now, guys, I'm using terms. If any of you guys are in the audio or the audio, they call it sampling rate. Sampling rate is how many times per second do I look at the signal and take a sample of it. So maybe this, if I want to, I can sample at a higher rate, and then maybe instead of every hour or whatever the time is here, I sample in here, and so I'm adding more points. If that's not good enough, I can sample at a higher rate. I can add even more points. But there's a trade-off. What's the trade-off down here? Every time I add a point, remember, there's a digital code over there that's got to store that point. So
take up more data.
Yes, you're getting more data, and the part we're not saying is you're getting more data. So number one, we need more storage, and number two, that data doesn't stay in one place. You're going to move that data around in the device and maybe even outside of the device. Maybe you're going to transfer it from one place to another. So the higher the term I want to use, I've been avoiding it. It's called the resolution. The more you sample the analog signal, the higher the resolution. So the higher the resolution, the more codes I'm going to need to store it. If I want to move it from one part of the computer to another, or one part of the network to another, it's going to take more time. So it's a trade-off. So usually there's kind of some kind of healthy balance to say you want to balance the resolution against how much information you're throwing away. So that term resolution is important. How many times do we sample the signal? And you know, I'm running out of time here, but think of your cell phone completely differently now. Just think about it. You can you're talking to your cell phone microphone. It goes in as analog, but it's going through this process. When it goes to the microprocessor in the phone, it's stored as digital. You take a picture with your cell phone, it's a digital picture. Instead of dots, they use pixels, but each pixel in that picture, which is analog like a Polaroid, when it goes into that phone, each pixel, each part, each dot is given a binary code. Or if it's a movie, you shoot a video with your cell phone, it's the same thing. Inside, if you can open up the circuitry in your phone and look at it, all you would see is zeros and ones. You couldn't tell what was a picture, what was a Word document, what was a video. It all looks the same. And it's amazing that we can take that stuff and reassemble it back into a graph or sound or video, but that's the way it's done. So guys, I got a little bit off topic. I'm out of time. I see it's almost 2 o'clock. But hopefully, you know, you got an appreciation now. The reason we have to talk about this is because what we're going to do is this. In the old days, they would actually wire up relays in series and parallel, and I'm here to tell you it was a wiring nightmare. And every time something changed, you have to get electricians to come in and rewire parts of the circuit, or in some case, the whole control system. And most of when you have a control system, you have the logic part of it, and then you have the electronics that's actually controlling the system. Well, 85 to 90% of all the wires is just for the logic part of it. So it was a wiring nightmare. Well, now with the PLC, as you'll discover when you do your first homework, all of that, instead of taking actual switches and hooking them up like this to make an AND circuit, instead of doing that, or doing this to make an OR circuit and having a bunch of those together to have some kind of complex logic circuit. All of this now is done in software. All of this, you would actually, we don't use switches, and we'll talk about what you actually do use, but you'll use software commands or software instructions to represent AND logic, OR logic, not logic. And this, you'll see it's pretty simple, and actually it's pretty interesting the way it's done. So we'll get to that. I'm out of time now, so I got a little bit off track, but hopefully you guys got something out of this. Anybody have any questions or comments for me before we sign off?
I have a question about the software.
Okay. Oh yeah. What's your question?
Just like when I looked it up to purchase it, I didn't really see like I saw a bunch of websites, but they're all kind of like shady. So would you have like a recommendation?
No, go to it's called the Learning Pit. The Learning Pit. The Learning Pit. And it's called Logix Pro. Logix Pro. And it should be, I think it's around $30, $30 or $40. Now you won't need it right away. You won't need it for like 4 weeks. But if you want to go ahead and play around with it, that's fine. You know what you can actually do, guys, if you want to? You can go here and you can download free for 15 days. You can download it and fool around with it if you want to. And then when we get to the lab time, you can just pay for it, activate it, because you'll need it. If you download, you can't use the free copy through the course because you got to do stuff in there that they don't allow you to do with the trial version that you download for free. But you can download it like today and look at it for free for 15 days and play around with it. And then when we get ready to do the lab, you just some kind of way you pay it and they'll activate it for you, and it won't be a trial version anymore. So go to this website, the Learning Pit. And if you have any issues or trouble finding it, send me a text and I'll send you a link that goes directly to that. Anybody else? Okay, guys, thank you so much. Have a good rest of the day. I'll see you guys on Friday. Bye-bye.